Ever nudge an old round thermostat and hear a click? That click is a coiled metal strip bending just enough to tip a tiny switch. That tip tells your heat to turn on or off. It is simple, clever, and it ran millions of homes for decades. Take that classic Honeywell Round on the wall. Inside, the entire brain is a shiny spiral and a small glass capsule. The spiral feels the room. As the room warms, the spiral slowly turns. At a certain point, gravity helps a switch flip. Your furnace hears that and responds with a hum and whoosh. We will open it up in your mind. We will watch temperature turn into a mechanical nudge and then into a very satisfying click. This is everyday engineering at its most neat and tidy. Here is the hidden problem. A home is not a lab. Furnaces heat up slowly. Rooms hold heat like a big pot of soup. Drafts lie. A sunbeam cheats. If a thermostat chased an exact number, it would overshoot, then swing back, then overshoot again. Hot, then cold, then hot. Think of a shower handle. You twist for warmer, wait, then it gets too hot, so you twist back, and now it feels chilly. That bounce is what a thermostat must avoid. It needs a way to hold a steady comfort without constant fiddling. So a good thermostat uses stability tricks. It allows a small comfort band instead of a razor-thin line. It also gives the system a gentle head start, so the room coasts into the target instead of blowing past it. The old rounds did both with pure hardware. Let us build the sensor from scratch. A bimetal strip is two different metals bonded together. When metals warm, they expand. Different metals expand by different amounts. Bond them, and the side that expands more tries to grow longer. The other side holds it back. The strip bends. Here are some real numbers to make it feel solid. Brass grows by about 19 parts per million per degree Celsius. Carbon steel is about 12. Invar, a special alloy, is about 1.2. Pair a high expander with a low one, and you get a reliable bend for every degree change. A straight strip only moves a little at the tip. So the thermostat wraps that strip into a spiral. Now a small bend becomes a visible turn. A tiny rise in room temperature makes the coil unwind by a clear angle you can see if you watch closely. There is a fun museum demo for this. Hold the loose bimetal coil in a clamp. Warm it with a hairdryer. You can watch the coil slowly unwind. A small lever lifts. That is the exact motion that once commanded a whole house furnace. Inside the round thermostat, the end of the spiral connects to a tiny lever. Your set dial shifts the lever's tip point. The spiral turns with the room. The lever waits for that one exact angle where the switch flips. You feel it as a crisp click when you move the dial. Now the switch. In the classic models, the lever tips a small glass vial that holds a few grams of liquid mercury. Tilt it one way, and the shiny droplet rolls to bridge two contacts. That completes the signal. Tilt it back, and the droplet rolls away. The circuit opens, heat stops. This is why installers carried a bubble level. The switch used gravity. A degree or two of wall tilt could change the temperature where the flip happened. Leveling the base was part of the job. It was not looks, it was function. Electrically, the job is simple. Most homes in the United States used a safe, low-voltage loop. About 24 volts AC runs through small wires in the wall. When the thermostat closes the switch, it completes that loop. A relay or a gas valve hears the call for heat and starts the burner or fan. There is another trick to keep things calm. The thermostat builds in a small deadband. That means it will not turn on and off with every tiny wiggle of temperature. In many homes, that band is about 1/2 to 1.5 degrees Fahrenheit. Enough to stop chatter, small enough to feel steady. The mercury vial helps with this too. The droplet does not smear on and off. Surface tension and the glass angle make it snap from open to closed with a clean gap between the 2 points. That gap is hysteresis. It is the space that keeps clicks from buzzing. But even with a deadband, heat takes time. If the thermostat waited right until the room hit the set number, the furnace would still be blasting, and the room would overshoot. The old rounds fixed that with a tiny heater inside called a heat anticipator. The anticipator is a little calibrated wire loop near the bimetal. When the thermostat calls for heat, a small current also warms this loop. That gently warms the bimetal early. So the thermostat turns the burner off a little before the room reaches the target. The room coasts the last bit. You could tune this nudge. On the classic Honeywell Round, a small sliding pointer sat beside the anticipator. It was labeled in amperes. Think roughly 0.2 to about 1.2 amps. You matched it to the actual control current of your furnace, so the preheat felt just right. Here are a few wall stories that make this real. Tap or warm a classic round with your hand, and you might hear the furnace click off early. You just fooled the bimetal and the anticipator with a tiny bit of local heat. It is that sensitive. Service techs use this on purpose. If a hydronic system was slow to respond, they might slide the anticipator from 0.2 toward 0.8 amps. That made burner runs longer and steadier. Comfort changed right away with one small tweak. Leveling the base was just as important. Drafts and sunlight matter too. A cold leak down a hallway or a warm sun patch on the thermostat can lie to the sensor. The bimetal only knows the air right around it. Good placement on an inside wall, away from vents and windows, helps a lot. Not every region wires heat the same way. The 24-volt loop is a United States habit for much of the last century. In parts of Europe, thermostats often switch mains voltage. The idea is the same. A small signal tells a larger machine to work. The wiring details differ. Modern thermostats moved from coils to chips. Today, a tiny part called an NTC thermistor senses temperature. That stands for negative temperature coefficient. Its resistance drops as it warms. A common type measures around 10 kilo-ohms at 25 Celsius and is accurate to about half a degree out of the box. Software replaces mercury and the anticipator. The code adds a deadband and filters noise. It also targets how many cycles per hour fit your system. For forced air, 3 to 6 cycles per hour is common. For hot water boilers, 1 to 3 suits the slower thermal mass. Even before full digital screens, some later mechanical rounds dropped mercury. They used a snap-action microswitch with a little magnet to help it flip cleanly. Same idea, clean on, clean off. No hazardous material inside. This bending metal trick shows up all over the house. Your toaster uses a bimetal to know when hot toast is done. Many kettles use it to pop off at a boil. Simple, robust, cheap, and surprisingly precise when tuned. No numbers needed for breakfast or a warm room. Step back and admire the scale of this. Henry Dreyfuss designed the Honeywell T87 in the 1950s. It sold in the tens of millions. It quietly ran heat across America for decades, all from a coil that bends a fraction of a millimeter and tips a droplet of liquid metal. If you enjoy clear looks inside everyday machines like this, you will like the rest of Buildguts. We do engines, bridges, chips, and the power grid, all in plain words. Subscribe and drop a like if this was useful. There are more deep but friendly tours waiting on the channel. Thanks for watching and see you next time.